There are many different types of forces that we learn about and use in physics. A force is a physical quantity that characterizes the interaction of two objects. A force is a vector quantity and represents the symbol F. Lastly, forces have agents, and when we look at them in the point-particle model, objects cannot exert forces on themselves.
Applied force is a force that is applied to an object by another object or by a person. The direction of an applied force is a push or a pull. The symbol used for this force is Fa. An example of this would be a person is pushing the chair across the room. The FBD diagram for this force would be like this. Normal force is a force exerted upon an object that is in contact with another stable object. Usually a normal force is applied horizontally between two objects in contact. The symbol used for this force is Fn. The direction of the force is perpendicular to the surface. For example, a book is resting on a table. The FBD diagram would show that the normal force is pointing up. Friction force is an object that moves across a surface which causes friction. Friction force can be sliding or static. Friction depends upon the nature of two interacting surfaces. The direction of the force is opposite to the motion of the direction. The symbol used for friction force is Ff. For example, a ball rolling across the floor. The FBD diagram that we draw for friction force would be like this. Tension force is a force that is transmitted through a string, rope, cable, or wire. When it is pulled tightly by the object on the opposite ends of a tension force. This force flows across the length of the wire or rope. The direction of the force is opposite the motion of the direction. The symbol used for tension force is Ft. For example, you have a cable car climbing the mountain. So for your FBD, the tension would be going that way because the tension is being pulled from right here. Air resistance or drag force is a different type of frictional force that acts upon an object as they travel through the air. The force of air resistance or drag forces always opposes the motion of the object. It is clearly recognized when an object travels at high speeds or when the object has a large surface area. The force direction is opposite the motion of the object. The symbol used for air resistance or drag force is Ft. For example, you have a person that's skydiving using their parachute to slow down the fall. So for your FBD diagram, your air resistance or drag force is pointing up. Gravitational force, also known as weight force, is the force by which the Earth or Moon or other massively huge objects attract other objects towards them. An object on the Earth experiences the gravitational force, which is directed towards the center of the Earth. The force of gravity is always equal to the weight of the object. The force direction is in the direction of the pole. The symbol used for this is Fg. So, for example, the Earth's gravitational force is on a person, which means it's pulling them down. So the FBD diagram would be spring force is the force which results when a spring is stretched or compressed. A spring force is a metal elastic device that returns to its original from where it's pulled, extended, or pushed, compressed. If the spring is stretched, force is attractive. The direction of this force is followed in the direction of when it's pulled. The symbol used for spring force is Fs. For example, when an elevator collapses, the safety springs on the bottom will make sure that the elevator itself will not impact the ground, which means that they're going to go back up. The FBD diagram for this would
Weight and mass may sound like the same thing, but they're very different. Mass is the quantitative measure of inertia, where weight is the measure of the amount of force acting on mass due to the acceleration of gravity. The SI unit for mass is expressed in kilograms, grams, and milligrams. The SI unit for weight is expressed in newtons. Mass is measured using a pan balance, triple beam balance, lever balance, and electronic balance. The formula used to find mass is m equals Fg over g. Weight is measured in using spring balance. The formula used to find weight is Fg equals mg. Mass is scalar, which has magnitude. Weight is a vector quantity, which has magnitude and is directed toward the center of the Earth and other gravity. The weight of a body changes its force near the Earth, where mass is the same everywhere. The weight of a body is the force that causes it to be accelerated downward with the acceleration of gravity at g equals 10 meters per second squared. When taking an object to a different planet, the weight will change because of the difference between the gravitational changes between the Earth and wherever else in space the object is. However, in terms of mass, the mass will stay the same because mass is the amount of space that an object will take up. Mass is meant to stay the same between all possible locations that an object is located in. An example being, a 55 kilogram raccoon will have a weight of 550 newtons on Earth. If you take the raccoon to the planet Gallifrey, which has a gravitational acceleration of 1.5 meters per second, calculate the mass of the raccoon. So for the example, we're going to be finding the mass, and we know that the force of gravity is 550 newtons, and that the g will be 10 meters per second squared. We have 10 because mass doesn't change on any planet due to gravity, that is the weight. So for the equation, we'll be using m equals Fg over g. With the substitution, that turns into m equals 550 over 10. And so then the answer is mass equals 55 newtons. Newton's first law.
Newton's first law states an object at rest remains at rest and an object in motion remains in motion with the same velocity unless acted upon by an unbalanced force. It is the natural tendency of objects to resist changes in their state of motion. This tendency to resist changes in their state of motion is described with the term inertia. Inertia is a property of mass by which it continues in its existing state of rest or motion in a straight line unless the state is changed by an internal force. So for Newton's first law, the example is a box is suspended from the ceiling, which for your FBD diagram, you're going to do Ft because it's hanging from the ceiling, so it's tension, and then Fg for the bottom. And the next part is what's the net force equation. So for the net force equation, you do sigma F equals Ft minus Fg, and because it's constant, it equals 0. And then the next part asks, If the gravitational force of the phone is 23 newtons, what is the tension force? And to start, we fill out our data, which is Fg equals 23 newtons. And then we're looking for Ft, which we don't know. And then our equation is going to be Ft equals Fg. Because to get that, you add g to both sides, and then to fill it in, it goes Ft equals 23, and your answer would be Ft equals 23 newtons.
Newton's second law.
Newton's second law states that for a particular force, the acceleration of an object is directly proportional to the net force and inversely proportional to the mass of an object. The direction of the force is the same as the acceleration. The equation used for this force is A equals sigma F over m, or sigma F equals ma, which is mass times acceleration. So the example we're using today is the 3.5 kg mass is lifted with a tension of 55 N, which is newtons, in order to accelerate it. So to start, we're going to look here at our FBD diagram, and you have a box that's being lifted up. So that's where you get your tension, and then you're always going to have something going down, which is your gravitational force. After that, we're going to look for our net equation, which is sigma F equals Ft minus Fg, which equals ma. Then, because we want to know what the acceleration on the mass is, we divide m by both sides, where we get a equals Ft minus mg over m. So then we're going to write all our data out, which a equals question mark because that's what we're looking for. Then you have g, which equals 10 kilograms, mass, which is 3.5 kilograms, Ft, which is 55 newtons. So then after we write all our data out, we write the equation, which is A equals Ft minus mg over m, where we have to, after that, we plug in the numbers. So you get A equals 55 minus 10 times 3.5 over 3.5. And after you solve that, your answer, you get A equals 45 meters per second squared.
Newton's third law. Newton's third law of motion applies to two different forces on two different objects. The action force one object exerts on the other, and the equal but opposite reaction force the second object exerts on the first. Action and reaction forces never balance out because they act on different objects. According to Newton's third law of motion, when one object exerts a force on another object, the second object exerts a force on the first object as an equal force in the opposite direction. Newton's third law states that for every action, there's an equal and opposite reaction. Example 1 is that a car hits a person forward, but the person hits the car back. So we have example 2 is that a bird pushes down on a telephone wire, but the telephone wire pushes back up on the bird. Example 3, a baseball bat hits a baseball and forces the baseball forward. And a baseball hits the baseball bat and forces the baseball bat back. Example 4 is the rocket's direction is to push down on the ground with the force of its powerful engines. And the reaction is that the ground pushes the rocket upward with an equal force.